Okay, now we'll move to our next topic. Let me current sensing. Okay. So we already know from linear regulators why we need current sensing. So the main reason, we want to protect our device from short circuit or when the load becomes very high. So we want to protect MOSFETs, we want to protect our routings, metal, everything, because they have certain current rating, and the MOSFETs you have designed, they cannot cater more than certain current which you have designed for. So they will heat up and it may melt, or your devices may break, anything might happen. But in this case, switching regulator, we have inductor also. So we have to protect inductor as well from getting saturated. Okay. So we need to limit the inductor peak current from getting saturated, and we call it overcurrent protection, OCP. Okay. And another place where we require this current sensing, for current mode control. Okay. For current mode control, you need the current information. So we use the inductor current information to control the basically to build a current mode control switching regulator. So limit average power stage current within the maximum rated specification. So one is the peak, and so one thing you need to remember, if you have sized your MOSFET for a certain average current, then the peak current it can carry much higher. It may be more than 2x actually. Okay. It depends for how long it is. So if you have designed, let's say for 1 amp, maybe a transient current it can support 2 amp or so. Okay. So most of the time is the average current which may basically break your transistor. So if let's say you have designed for 1 amp current, if let's say for 3 or 4 cycles it goes, I mean the peak current can go 2 amp or so. So it won't break your device all of a sudden, I mean, because temperature rise will take some time. So unless your temperature goes very high and it melts your device and your routings, everything, it will not break right away, until unless your peak current goes to 10 amp or so. Okay. And most of the time we keep 1.5 to 2x of your load current, the peak current, we don't keep it 10x also. So another place where we require the current sensing is if I want to build a current regulator. And current regulator we already talked about, it's required for battery chargers and your LED drivers, because battery is supposed to be charged with a constant current, and LEDs also are supposed to be driven with a constant current, because it has the exponential relationship. You cannot just apply a constant voltage and say okay, LED will lit up. Even a small change in the LED voltage can cause a very large change in the current, and which means your brightness will change and it may even heat up actually, even if you change the voltage by 100 millivolt or so. So that's why it's always require regulated current. Then another place which may require, may or may not actually, depends on how you build your PFM mode. So we talked about how you enter PFM mode. One is a light load condition you can detect, or you can always detect the DCM mode, and right away when you enter the DCM mode you can enter PFM mode, or you can wait until your duty cycle is saturated. So these two do not require current information. You know when the duty cycle is saturated, and you also know when it's entering DCM. Okay. With the help of zero cross detect, you can know when it's entering the DCM, because we need a zero cross detect to detect reverse current. So that output of that comparator or zero cross comparator can always tell you when you are entering the DCM mode, and you can enter the PFM mode right away, or you can wait until your duty cycle is saturated, and that is also in your control. You know the control voltage. If it's a voltage mode, you know at what control voltage will give you 10% duty cycle, or you can literally measure the time also with the high frequency clock. You can measure, count that pulse width, and you know that this 10% duty cycle is this pulse width, and high frequency clock will count 10 or 20 whatever, and that count digitally you can implement. So you can enter. Or third option is you can look at the current, actual current, load current, and you can enter into PFM mode based on that also. Okay. So these current sensing can be based on peak current sensing or average current sensing. Okay, just like you have a peak current mode control and average current mode control. The third one, you have a valley current, but in case of sensing we do not require valley current, because we are more interested in the peak current, because we are protecting our devices. So the information obtained from peak current sensing can also be used for to calculate the average. So if I know the peak current, I know the ripple, then I can calculate the average current. That is very easy. Okay. So the average current is basically, you can say it's average, so it's a slower, you calculate the average over few cycles. If you can do the cycle by cycle average, then it's also okay, but if you are looking for average information, then you can wait for certain cycles and to get the average. But if you have a peak current information, then you can right away get the average value within the same cycle. Okay. So if you have a peak current sensing, then you can always get the average current, but if you have average current, then you cannot get the peak current right away, cycle by cycle. Okay. Even if you have, let's say you have a ripple information and you can add that ripple and get the peak current, but your average is taking time to calculate. So when the current changes, then your peak current information will appear late actually. It will not give you within the next cycle. So that's why peak current sensing is always done cycle by cycle. So every cycle you need to calculate. So if there is a change from one cycle to next cycle, you should be able to detect that. So we cannot wait for long time. So that should be very fast, that sensing circuit. Okay, so these are different methods for current sensing. Sense resistor based current sensing, which is nothing but you connect in series and you get the voltage across that. MOSFET RDS based, RDS on base, so it is also another type of resistor based sensing, but you are utilizing the RDS on in place of your sense resistor. Okay. MOSFET VDS based current sensing, observer, integrator based current sensing, RC filter. So these two we talked about in current mode hysteretic, if you remember. The RC, it's the same thing actually. So that contains the current information. If you choose your RC value properly, then it will give you the exact current information. Otherwise, it will have different. Then sense based current sensing and transformer based. So last one we hardly use in for on chip converters. This is mostly used in power electronics. So this is your sense based. So you connect a series resistor R sense with the inductor and get the voltage across that. This voltage divided by R will give you the current. So it's a very accurate. If your R sense, sense resistor can be very accurate actually. There are resistors which can be like even as accurate as 0.1 or 0.2% even across the temperature. So less than 1% accuracy you can achieve with this external sense resistor, and most of the time for battery charger and all those, this external sense resistor is used, because you cannot get better accuracy than this. But the problem is efficiency. There will be I square R loss here. So the example is like if a R sense is 100 milliohm and for an output voltage of 1.8 volt and load current 1 amp. So the loss here will be roughly 5% I square R loss. Correct. So that's why for efficiency purpose it's not good, but if you are looking for very high accuracy, then you can go for it. Then RDS based sensing. So what you do, instead of that detecting this voltage across this resistor, so let's say we don't have this, then you have another resistor which is the RDS on of your MOSFET. So if I can detect this voltage, and that you can always do, when this switch is on, you just measure the voltage across this, and if the RDS on you already know is this, then you can get the current information. But the problem is this RDS on is not fixed. It will vary with the temperature, because threshold voltage may change with the temperature. So, and process may also cause some variation. Okay. So this vary with the PVT and it's not very accurate. So, and even it vary with the voltage, because it has a VGS here. So how much voltage you are applying across gate to source, that will also determine your, and this is a NMOS, but let's say if a PMOS, then you connect, when you are turning on, you connect to ground, let's say VDD is changed, So VDD is changed, which means VGS minus VT is changed. Then you will get different RDS on and it will change everything. So accuracy is not good unless you have a way to basically calibrate this RDS on and across your process voltage and temperature. So this one is much better. This is sensing VDS instead of sensing the RDS. Okay. So what you do, I have a replica of this. When I say replica, so let's say this guy is 100 milliohm, I have sized it for 100 milliohm, but this is much smaller. Okay, so if it, let's say 1000 times, then it will be 1 unit. So 1 is to 1000 or 1 is to 10,000. So if I want to generalize it, I will call it this is n times larger than this. And so I have this standalone, and what I am doing, I am feeding a current IREF. So when this is turned on, so this gate is driven by the same voltage as this. So which means when you are turning on, this is connected to ground or not ground basic. If it's any other voltage, then that will appear here. So it's better to have a same voltage here. So and Vin is also same. So we are turning on. So both are operating in linear basically when they are turned on. And so this guy will carry I load current, and this guy will carry IREF current, which is fixed. So this voltage is fixed, which I called V sense, but this voltage may vary, and this voltage will vary for what? No, let's say with the, let's say RDS on is fixed, then I load will change this VDS, correct? So if I sense this VDS and take the ratio of the two, that will give me the load current. So IREF multiplied by the ratio of these two voltages will give me the load current. But let's say if this guy is changing, this RDS on is changed, but they are same devices. If this is increasing, this size also increase. So that effect is cancelled out actually. So the variation with PVT is cancelled out because they are same type of devices. What temperature is seen by this guy will also see the same temperature. Okay, and both have the same formula, which is this, correct? The only difference is W by L is different. Rest of the parameter will remain same. So the only size will determine the voltage here, and here the load current will determine. So if you look at the ratio of the two, then those PVT effect will get cancelled out, and that's what we have done here. So your IP is nothing but VDSP over RDS, and IREF is V sense over RDS of this. Okay, and the ratio is this. Okay, and RDS on of this sense is n times of RDSP. You substitute here, and that's what you get. So what information you need? You need IREF. IREF is already known because it's a fixed current you are feeding here, and you need these two voltages, and you need to take the ratio of the two. Okay. So which means, I mean, it's not that straightforward. You cannot divide these two voltages in analog. It's not that simple. So most of the time it's done digitally. So what you do, you take this voltage and this voltage, have an ADC. From ADC you generate these two codes and divide the code, and then multiply it by this n times and IREF, you will get the load current right away. Okay. So this is a very simple method and very decent accuracy you can achieve, and most of the time you don't require, you may not need a dedicated ADC for this. You may already have a ADC in system which you can utilize if you are not looking for peak to peak. For average current, because once in a while you want to measure, okay, average current can be slower, but if you are looking cycle by cycle current, then you require dedicated ADC. Okay, and you can do with a single ADC also. Let's say if your ADC is fast enough to basically convert this analog into digital within one PWM cycle. So one PWM cycle you can measure this IREF, another PWM cycle you can measure this. So at least every alternate cycle you can get the peak current. Okay. So with one ADC you can do. Same thing you can do with the NMOS. if you are looking for a valley current. And once you have both peak and valley, if you add the two, you will get the exact inductor current, and you can get the average current from there as well. Okay. So, this is your observer based sensing. So, we know that inductor is nothing but the current, inductor current is integrated version of your voltage across it. So, what you do, we take the voltage and put another integrator and multiply it 1 by L, which is the gain of integrator, you can say. So, you will get the same current here across. But this is only true if there is no loss in the inductor radial. The moment you have a loss, this integrator will saturate. Okay. So, it is very difficult actually, and another drawback of this is this 1 by L is different than this, because this is the integrator gain and this L. So, you cannot track the two. So, you need to have a way to measure the inductor value and tune your gain, integrator gain accordingly, only then you can get accuracy, and this will work under no loss conditions. So, which means you can get the peak current, the ripple current, but DC current is very difficult because your integrator will saturate. So, this is another one, GMC is the same thing actually. So, if you want to implement with the GMC, and we talked about this in hysteretic converter, if you remember. So, this will not work if you have a loss under load condition. So, because your integrator will saturate. So, you can get the ripple information under zero load, but the moment you apply a load, you will lose all the information. Okay. So, that is why I am saying here works only with the zero loss across the inductor. So, you can use it for a ripple information, and you can reset the integrator every cycle, so that it will not saturate. And if you remember, we did it by connecting a switch in parallel with this, and you reset every edge of the clock. So, you can get the ripple information, and that is also if your gain of integrator is same as inductor, like 1 by L. So, this condition you have to meet. Okay. So, L is nothing but C by GM. If you match this, then your ripple information you can get. So, this is RC filter based sensing. Another same thing which we used in hysteretic, current mode hysteretic, if you remember. But here if you see, you have both the information actually, ripple as well as the DC. So, if you look at this, this is nothing but low pass filter, correct. So, what is the voltage across this capacitor? So, there is no loss in this resistor, which means this voltage if you integrate or pass through a low pass filter, so the DC voltage here and the DC voltage V out will give you the difference drop across RDCR. So, which means if I measure the voltage across the capacitor is nothing but voltage across RDCR, and if I know RDCR, so I can take this voltage difference and divide by RDCR, I can get the DC information, and this ripple will give me the Vx will give me the, okay. So, when Vx minus V out you do, you have both the components, you have a ripple, because if you measure at a Vx, it is a triangular waveform we looked at, and V out is pretty close to DC. Now, if your Vx is much larger than V out, that was the condition for your current mode. Here also, like you cannot keep Vx too small that your V out ripple will basically kill this voltage and you cannot get any information. So, you want to make sure that this is large enough. Okay. So, this delta L will have a k times delta Vc. K times is nothing but depending upon how you choose the RC time constant compared to this, that will give you a k factor. Okay. So, if this is let us say 100 milliamp peak to peak, you can have a gain factor here, make it 500 millivolt peak to peak. So, the one difference is this current gets converted to voltage here in this RC filter. Okay. So, you will have the same information, one is the voltage DC voltage and the ripple will be voltage, not the current, but that same inductor ripple current will get mapped into voltage here. and if you have a RC time constant same as your match with the inductor, then your voltage will be, peak to peak voltage will be same as peak to peak ripple current. So this can give you, the only problem here is this RDCR doesn't remain fixed, it can change with temperature. Okay. So that's the only drawback, otherwise it's a very good technique to use a current sensing without any loss here, because you don't require any series resistor here. So you can get both ripple as well as DC information here. Okay. So if you choose RF CF equal to K times L, then ripple voltage across CF provides the ripple current sensing, and K should be chosen such that RF CF is much larger than TSW, because we are looking for a triangular waveform, not exponential. Okay. We don't want to have any non-linearity, because we are replicating the inductor current into the ripple voltage here. So this is SenseFET based current sensing, and this is most commonly used if you require very good efficiency and very high accuracy. So what you do actually, it's a current mirror here, SenseFET, but since this is operating in the linear, so in the current mirror actually if you have a VDS mismatch and channel length modulation is not very high, then the current is almost same. But here in a linear, even a small change in the voltage can cause a huge change in the current. Okay. So which means we have to match both VGS and VDS, and that's what we do here. So we are having this if this is n times and this is 1x, so again 1:n ratio here, so which could be 1000 to 10,000 times. So and if I have, let us say this current is nothing but this current divided by n, because if VDS is matched and VGS is matched, then the current will scale according to the W by L size of this, the ratio of this, which is n here. So this becomes IL by n, and you dump into a resistor, you get the V-sense voltage. So voltage to current converter. So this voltage will contain the information of the current. Okay. So how we implement it? This is how we do it. So this is VSW, this is VSW. So when this guy is on, it will have a IR drop. Okay. So this will be V in minus whatever IR drop, and we want to keep this drain voltage same. So what you do, this is regulated cascode actually. So VSW, and this feedback will force this node to be same as VSW. So now this will see the same VDS, V in minus VSW, which is seen by this guy when this FET is on. So now you have matched both VGS and VDS. So this will carry the same current I sense equal to IL by n. So now you can match the current, but the problem here is like you want to do it every cycle, cycle by cycle. So this amplifier should be very fast, and gain should also be very high. If you have a very poor gain, then this voltage will not match. You will have a gain error, large gain error. So which means the both gain and bandwidth has to be very high. So it's not very easy to implement, especially if you, let's say I am sensing, I am let's say the gain bandwidth of this I have kept very high according to 50% duty cycle. Now assume what will happen if the duty cycle goes to 10%. Your current will rise much faster. So now this guy has to track this voltage much faster. So the bandwidth of this should be based on the maximum slope actually of the current. Okay, so another sources of error could be here, like obviously the offset, and if you have limited bandwidth, what will happen? It will not track, so that will again give you the error. Okay, so I mean I am looking here, I mean this is a ramp actually. If you look at the voltage difference, is a ramp, because current is ramp, current is rising, so voltage will be ramp here. So this has to track that ramp, and if I am not able to track properly, which means bandwidth is smaller, then I will always have some delta error, and that error will cause a difference in the current, so accuracy will go bad.
High duty cycle only there will be a fast shoot in current.
Why?
Like when duty cycle is 90%, then only due to high slope, there will be
No,
fast change.
higher duty cycle means how your V out is high, huh? So V in minus V out difference is smaller, so it will current rise will be slower, huh? Okay, so another mismatch between these two FETs, that mismatch will come from layout mainly. So most of the time we try to match these very closely, which means you have to place them very close. If you use a single device, it's very hard to match. I mean, this guy is 10,000 and that guy is 1. You don't know which corner you will keep to match it. The best way you have to keep it at the center, huh? Only then you can match on an average. So most of the time what we do, instead of a single device, we use 10 or 20 devices of this and we spread around. So you keep at all the 4 corners in between center. On an average, you can get a very good matching. Okay, so the advantage here is like everything is fully integrated, no external components is required. It's a lossless. When I say lossless, there is no additional loss in the current path, and this is very small. So if you look comparing, this is a milliamp of current compared to amp here, so it will be. So current transformer we never use actually, because it's a bulky, it cannot be built like on chip, so that's very bad. So but this is the most commonly used in MOSFETs. Okay.